We're almost halfway through the lectures. This is lecture 12 of 24, and we've learned an awful lot about the universe. Let's summarize what we've learned so far. We know first that the universe is big and it's getting bigger. By big we mean not only do we live in a galaxy, the Milky Way galaxy, with about 100 billion stars, but we live in a universe which is evenly distributed with galaxies, and a typical galaxy outside the Milky Way also has 100 billion stars. And there are maybe 100 billion such galaxies in the observable universe, so it's certainly big by any standard. It is getting bigger, which means the galaxies are moving apart from each other. We can understand that in terms of Einstein's general theory of relativity. The space in between galaxies is itself expanding, pushing galaxies further apart from each other, and stretching the wavelength of light as it travels through empty space, giving rise to the cosmological redshift. We also have a universe that is full of stuff, but interestingly, there's more stuff in the universe than what we see. We can weigh things in the universe. We can figure out how much mass they have using their gravitational fields. So we can take an individual galaxy, we can weigh it by looking at the motion of stuff outside the galaxy. What we find is that there continues to be more and more stuff in the galaxy even when you can't see stuff anymore. Even when the visible parts of the galaxy stop, there's still more and more mass as you go further and further out. This is evidence for dark matter. This evidence is enhanced by looking at clusters of galaxies, at collections of galaxies moving around each other. You can both look at how fast they're moving to measure the total mass. You can look at the lensing of light that passes through the cluster to measure the total mass. You can look at the profile of X-ray gas in between the galaxies to measure the total mass. Any one of these methods gives answers that are consistent with each other, and answers that the total amount of mass in the universe is something like 30% of the critical density you would need to have to make the universe spatially flat. So 30% of the universe is 30% of the critical density is a lot more than we can account for in terms of ordinary matter, in terms of the particles that we know from the standard model of particle physics that make up protons, neutrons, and electrons, the ordinary atoms of which I'm made and this table is made and everything else is made. How do we know how much ordinary matter there is in the universe? I've been emphasizing throughout the last several lectures that we have independent ways of measuring the total amount of ordinary matter in the universe. Two ways in particular. We have primordial nucleosynthesis, Big Bang nucleosynthesis, the process by which when the universe was 1 minute old, it was converting protons and neutrons into helium and other light nuclei. The efficiency with which that happens, the percentage of helium you end up with at the end of the day, depends very much on how many protons and neutrons you have lying around. The more you have, the more helium by weight you will end up with. So the fact that we have a certain amount of helium, about 24% of the universe, of the visible mass in the universe by weight, means that only 5% of the critical density of the universe can be made up by ordinary matter. That's not enough to account for all the mass we need. Completely independently from that claim, we have the cosmic microwave background. We have slight variations in the temperature of the radiation that comes to us from when the universe first became transparent 400,000 years after the Big Bang. These slight variations in temperature are all statistical, they're random fluctuations, but different sized regions evolve differently. Some of them will be enhanced in their temperature fluctuation by moving towards dark matter. Some of them will be suppressed by pulling away from the dark matter, depending on how big that sized region is. So by looking at the distribution of different sized spots on the cosmic microwave background, we can infer that there must be dark matter pushing and pulling the ordinary matter we see. We get a consistent answer. It's consistent with the claim that 5% of the critical density is ordinary matter, 25% is dark matter. There are other ways of getting similar results, ones that we haven't talked about. For example, you can start with the microwave background, assume that this is telling you about the primordial perturbations in density, and then letting those density perturbations evolve to today, to turn into galaxies in large-scale structure. You can do this both with pencil and paper, and you can also do it with giant computer simulations. What you find is that in order to make as much structure as we observe on small scales mean galaxy-sized scales, it must be the case that there is dark matter in the universe, dark matter over and above what we observe. So many, many lines of evidence are pointing us to the conclusion that there's a lot of stuff in the universe that we don't observe directly and that cannot be accounted for by ordinary atoms, ordinary things that are neutrons, protons, and electrons. We need some form of dark matter. Today's lecture, we're going to get down to the nitty-gritty and talk about what the dark matter could possibly be. Now, the answer that we think is right is that the dark matter is some new kind of particle, some particle that is not in the standard model of particle physics, but is evidence for new physics that we haven't yet detected in the laboratory. However, I want you to trust me. I want you to not think I'm pulling something over on you. So today, we're going to consider carefully whether or not we might have made some mistake. Is it possible that the dark matter that we need to explain the motions of things in the universe might somehow be in the form of stars or gas or dust, collapsed objects that we don't see because they're just too small, but they're still made of ordinary stuff? We're going to say at the end of the day there's good reason to not believe this is true, but we want to go through the possibility because some of the ordinary matter in the universe is in fact dark. Some of that 5% of the critical density, some of the protons and neutrons, we know we don't see. We don't see the air in this room. We don't see different forms of gas and dust in the universe. In a cluster of galaxies, which we think a cluster of galaxies is big enough to be a fair sample of the universe, we know that most of the ordinary matter is in between the galaxies. How do we know that? Because in the cluster, there's so much stuff that it falls together, heats up, and emits X-rays, and you can observe those X-rays. So you know that in a cluster, most of the ordinary matter is not in the galaxies. 2/3 of it is in between. We believe that clusters of galaxies are fair samples of the universe, by which we mean the ratio of stuff in between the galaxies and stuff in the galaxies should be the same, outside a cluster and inside a cluster. So we believe that even if you have stuff that is outside clusters of galaxies, most galaxies in the universe are not in clusters at all, they're by themselves. We believe that it still should be the case that something like 2/3 of the ordinary matter in the universe is not in galaxies, not shining brightly in the form of stars, it's in very dilute gas in between. But nevertheless, we think that even taking that into account, we don't have enough stuff to make up the dark matter in the universe. So today, we're going to talk about different ways in which you can take ordinary matter and hide it in ways that are not very obvious. In yet other words, we're going to talk about dark baryons, stuff that started life as protons and neutrons, but has come into a form where it's not shining and is easy to see, but is hidden from us somehow. The simplest way to do this is to imagine that we have dark stars. A star that is a visible star, a bright star, starts life as a collection of gas and dust spread across some wide region of the universe, but it's a little bit more dense than its neighboring regions. So just like a galaxy is formed when a whole bunch of stuff comes together under its mutual gravitational pull, stars are formed when stuff comes together under their mutual gravitational pull in a much smaller region of space. The same kind of process happens, but with stars, life is actually much more complicated. The process of star formation is one that astronomers don't claim to understand very well. It's a very active area of research in astrophysics right now, because somehow when this cloud of gas collapses, it heats up, but instead of bouncing back under the pressure force, it fragments into little tiny stars, and somehow this involves not just the gravitational dynamics of things collapsing, but things like magnetic fields and atomic physics and the different ways that radiation travels through collapsing gas and dust. It's not a process we claim to understand. What we can do is go out and look at the end results of those processes. What are the kinds of stars that we actually see in the universe? The stars like the sun that we see are easy to see because they're shining, they're giving off radiation. That's because these stars are so massive that at the center, the hydrogen from which they are formed is being fused. Just like in the Big Bang, you're taking hydrogen, protons, hydrogen nuclei, and they're fusing together, and when you take hydrogen and turn it into deuterium and then into helium, you give off energy. The total mass of a helium nucleus is less than the sum of the masses of 2 protons and 2 neutrons. So it's able to give off energy by E = mc². So The question is, are there things like stars, things that are collapsed collections of ordinary matter, of gas and dust and so forth, yet are not shining? Maybe they're too small to shine or something like that. Well, yes, there are things like that. And you want to ask, how many of them are there? What forms do they take? How do you get them? The simplest way is to start with an ordinary star. Start with a star that is burning its fuel and recognize that there's not an infinite amount of fuel to burn in that star. There's only a finite fuel supply, just like everywhere else. So a star will burn. The sun has been burning for about 4.5 billion years. It has about another 5 billion years worth of fuel left, but eventually it will give up. All of its fuel will be turned into heavier elements. If your star is low mass to begin with, the death of that star is fairly straightforward and calm. It just gives up. It doesn't have enough nuclear fuel left. In the latter stages, it becomes big. It becomes a red giant, becomes puffy, and it gives off mass slowly into the outer reaches of space, and the core just slowly settles down into what we would call a white dwarf star. This is a collection of gas that has been pulled together by its mutual gravity, but has used up all of its nuclear fuel. So when it uses up its nuclear fuel, the reason why a star is so big in the first place is because there's pressure created by the temperature that is created by that burning fuel. The burning nuclear fusion process heats up the interior of the star, and that's what keeps it big. When you've used up all the fuel, you don't have any pressure to keep it big anymore, and the star contracts. What is it that stops it from contracting? Well, remember way back when we learned about bosons and fermions, we learned that fermions have the property that you can't pack them too tightly. The same reason why this table cannot collapse is because the electrons that are in the atoms here are taking up space. The same thing will be true with a star. If you take a star and let it use up its fuel and just collapse, eventually it will become the most efficient way to pack the electrons and the protons and neutrons into a very, very, very dense substance. That substance gives you a star called a white dwarf. It turns out that the electrons are the particles that take up the most space. It's the electrons that define how big that white dwarf will be. It's the Fermi pressure, named after Enrico Fermi of fermion fame, that keeps the white dwarf from shrinking anymore. The laws of physics say there's just nowhere to go. You can't put those electrons on top of each other. If the star is slightly heavier than that, it will not end up as a white dwarf. If the star is slightly heavier than that, it can burn heavier elements into yet heavier elements in a way that a medium or low mass star doesn't have access to. In that case, what will eventually happen after it puffs up and becomes a red giant is that the core will violently collapse. Unlike a low mass star that just sort of settles down, massive stars undergo core collapse. Their cores go very, very quickly to a very small state, and the outer layers are blown off in a supernova explosion. Now later in the course, we'll be talking in great detail about how to use supernova explosions as standard candles to measure the acceleration of the universe. So right now I need to let you in on a complication. These supernovae are not those supernovae. There are different ways that stars can explode to become a supernova. This way that we're talking about now is a core collapse supernova, which is known as a type 2 supernova. Another way is what's called a type 1 supernova, and the type 1 supernovae, which we'll talk about in later lectures, are the ones that give us a standard candle, and those are the ones that we use to measure the acceleration of the universe. A core collapse supernova happens when a massive star has burned up its fuel, the core shrinks, the outer layers are exploded off. That's a type 2 supernova. So what happens inside? You might have thought, well, things collapse, they're going to form a white dwarf. That's what they can form because the electrons just can't be squeezed in anymore. It's true that the electrons just can't be squeezed any more tightly, but there's something else that can happen. Because you have a lot of energy in these particles, you know that at high energies, a proton and an electron can come together to form a neutron. So a neutron is a smaller particle than an electron. One of the miracles of quantum mechanics is that particles that are higher mass take up less space. So that's why atoms have sizes that are controlled by their electrons, not by their protons and neutrons. It's the light particles that take up the most space. So if you want to squeeze things together, but you're prevented from squeezing them because your electrons are taking up space, you do have an out. You have an equal number of protons as you have electrons, because your star is electrically neutral. So those protons can come together with the electrons and form neutrons. The neutrons take up less space, so if you turn all of your electrons and protons into neutrons, you can get a much more densely packed object, and that object is called a neutron star. A neutron star is just a collection of particles that have all been turned into neutrons, and it is so dense that if you start with a several solar mass star, you can turn it into a neutron star that is only tens of kilometers across, the size of a city here on Earth. A very, very dense, high gravity situation. So you have two different possible end states for big stars. If the star is big but not too big, it will end up as a white dwarf. It's white because the surface of the white dwarf is still pretty hot, so it gives off some light but not very much. White dwarfs are actually very dim. If they're far away, you would not be able to see them. They would be candidates for somewhat dark matter. Neutron stars are very dim. Neutron stars are not giving off a lot of energy. They would also be candidates for dark matter. Finally, what if you had very low mass stars? Stars that were so low mass they were almost closer to being planets than to being stars. We have in our solar system gas giant planets like Saturn and Jupiter. These are not stars because they're not heavy enough to burn nuclear fuel inside. You can imagine objects that come from the condensation of gas and dust, but weigh, let's say, 100 times the mass of Jupiter. That is not heavy enough to turn on the nuclear fuel and start becoming a star. Such an object is called a brown dwarf. It is an object which is collapsed gas and dust, star-like in its initial stages, but never hot enough to begin burning, never hot enough to begin shining. So what that means is we have a whole collection of possibilities for ways to take matter, ordinary matter, and squeeze it down into some small, dense object that doesn't give off a lot of light. A white dwarf, a brown dwarf, or a neutron star. So together, these are all candidates for a certain kind of dark matter. Not non-baryonic dark matter, because all of these come from ordinary protons and neutrons. They started their lives as ordinary matter. They still count as ordinary matter in terms of nucleosynthesis or the cosmic microwave background. They're just ordinary matter hidden in a way that it's hard to find them. So people have invented a clever nickname for these compact objects. They call them massive compact halo objects, or machos for short. So last lecture we had WIMPs. This lecture we get machos. This is not an accident. People thought about this for years. So machos are a candidate for a way to take ordinary matter and hide it. To put it in a form where it would be hard to see, it would look kind of like dark matter. So I want to give you arguments that have nothing to do with Big Bang nucleosynthesis or the microwave background as to why machos are not a huge part of that 25% of the universe that we really think is not ordinary matter. Even if we didn't know from nucleosynthesis or the microwave background that the dark matter was not ordinary, could it be possible to rule out that possibility by looking at all the candidates one by one? I would like to argue yes. So first, let's consider white dwarfs and neutron stars. White dwarfs and neutron stars are dim. If, let's say, our galaxy was filled with many, many white dwarfs and neutron stars, they would act much like dark matter. They would be hard to see. They don't interact with each other, they don't run into each other that much, and they're very dense, so you can pack a lot of mass into these kinds of objects. The problem is that we only have very specific channels for creating white dwarfs and neutron stars. First, you have to make a big star. You have to make a star that shines. And that star that shines has to eventually give off its nuclear fuel and condense into a white dwarf or a neutron star. In the process of condensation, these stars give off a lot of mass. In fact, it's a minority of the original mass of the star that ends up in the form of the white dwarf or the neutron star. Most of the original mass of that star gets ejected into interstellar space. So if you're trying to imagine that the universe is full of white dwarfs and neutron stars, then you're imagining that there's all of this stuff that has been ejected into interstellar space during the process of forming these white dwarfs and neutron stars. And that ejected mass isn't there. That's stuff we would be able to see. That is stuff that would have heavy elements in it, stuff that would be affected in spectrum that we observe from different objects. It's just not there. So in other words, there's no way to efficiently take ordinary matter and convert any substantial fraction of it into white dwarfs and neutron stars. No way that we know of. For brown dwarfs, it's a little bit more complicated. The brown dwarf is not something that you get by the end of a star. It's something you create at the beginning as a very, very low mass star. So how do we know there are not a lot of brown dwarfs in the universe? Well, there could be, but our most reasonable extrapolations say that there are not. What you can do is, you can figure out how many stars are made as a function of their mass. You can observe the stars that we do see and say how many very massive stars are there, how many medium mass stars are there, how many not so massive stars are there, and from that you can extrapolate to how many brown dwarfs there probably are. It turns out that the most reasonable extrapolations we have say there shouldn't be that many brown dwarfs out there. Now, I'm the first to admit this is not an airtight argument. We could certainly very well be surprised. After all, if the alternative is new laws of physics, we should be thinking very hard. So, what we can do is come up with an absolutely new way of constraining the number of machos in the universe, regardless of how they were made. We want to go out there and look for condensed star-like objects, even without knowing where they could come from. The way to do that is to use gravitational lensing. Just like we used before to weigh galaxies and clusters, we can look for these tiny star-like objects using gravitational lensing. The good news about machos that lets us look for them using lensing is that they move. The amount of lensing due to one tiny little white dwarf, or one tiny little brown dwarf or neutron star, is very, very little. We would not be able to notice a big deflection of a background object. However, if we get an exact alignment, if a white dwarf is right in between us and a background star, what will happen is it will focus the light a little bit, and that background star will appear a little bit brighter than it would have without the lens. It's just like putting a magnifying glass up to the sun makes it look brighter if you're right there at the point where things are focused on you. The problem there is, of course, how would you know if something were right in the middle of you? And the good news there is that things move around. These star-like objects, these machos, are moving through the halo of our galaxy, or in between our galaxy and other galaxies, so we can look at a whole bunch of background stars at once and wait for events. Events where the macho goes in front of the background star, the brightness of the background star will be seen to go up and then go down. And it will do so in very specific ways. It will go up and down in a perfectly symmetric way, and it will go up and down in a way that is absolutely independent of what color you look at it. Every wavelength of light coming from that star will be amplified and then go back down again in precisely the same way. So there are projects going on to search for these micro-lensing events, and they have found them. Here is data from one of these projects. This is a light curve. This is the amount of light that is coming from a single background star. You observe literally millions of stars waiting for a coincident brown dwarf or white dwarf to go by. Here is the light going up and it's going down. It's perfectly symmetric. This is a wonderful candidate micro-lensing event. The point is, like I said, you look at millions of stars. You wait for these micro-lensing events. What you find is that there are not enough of them, there are not nearly enough of them, to account for what we need to be the dark matter of the universe. So it's not a matter of we don't know how to make them. If there were enough brown dwarfs, white dwarfs, or neutron stars to be a substantial fraction of the dark matter, you would have seen them using micro-lensing, and you don't. There is, of course, one other way to make very, very dense stuff in the universe, and that is a black hole. If you have white dwarfs as the endpoints of medium mass stars, neutron stars as the endpoints of more massive stars, you can then ask what happens if we squeeze those neutrons even more. Within the standard model of particle physics, there really is no place to go when you squeeze those neutrons. However, it is nevertheless the case that according to general relativity, something will happen if we keep adding mass to a neutron star. It can't last forever. What we think happens is it just collapses into a singularity where the gravitational field is so strong that light itself cannot escape. This is what we call a black hole. A black hole is the endpoint of gravitational collapse, where gravity is as strong as it can possibly be. There's nothing left after that. Now, black holes, you might think, would be hard to detect in the universe. After all, they are black. But we've told you again and again, there are ways to detect gravitational fields in the universe, even if the thing you're looking at that is creating the gravitational field is not directly visible. So ordinary matter spinning around a black hole can either be directly visible, or it can give off light as it's spinning. If you have a small black hole, the endpoint of a massive star, stuff that is spiraling into the black hole will heat up and give off X-rays. This is one of the primary targets for X-ray astronomy, is to look at accretion disks, as they are called, disks of gas and dust swirling around into a black hole, giving off X-rays as they go. There's another class of black holes called supermassive black holes that are 1 million or 10 million times the mass of the Sun. Supermassive black holes live at the center of galaxies, and we can detect them because what happens is that stars orbit them. So what you see is stars moving in an orbit, and you can actually make movies of these stars. You can see them going in an ellipse around nothing, around a region of space where there isn't anything there. And you know how far away these stars are, so you know how big their orbit is. You can measure the mass confined into a really tiny region. The only way you can put that much mass, over 1 million times the mass of the Sun, into a tiny region is for it to be a black hole. So there are stellar-sized black holes that exist. There are supermassive black holes that exist. Could either one of these be an important part of the dark matter? Well, the answer again is probably not. For stellar-sized black holes, all of the arguments that we used for machos still apply. Number one, we have no way of knowing how to make them. You could make them from stars, but that would eject a lot of mass. Number two, they would be machos. They would lead to microlensing events. We don't see enough microlensing events from black holes or from anything else to be a substantial part of the dark matter. But then we have supermassive black holes. Could the dark matter be million solar mass black holes? And so almost as I say it, you realize, no, probably not. Million solar mass black holes are hard to hide. It's true that you couldn't see any one of them, but if one of them is moving through a collection of stars, if it's not all by itself, it would cause a lot of disruption of the total dynamics of that system of stars. So supermassive black holes sit at the centers of galaxies, but they don't play an important role in the overall mass of the galaxy. It sounds like 10 million solar masses is a lot of mass, but remember that the mass of a galaxy is something like 1 trillion solar masses. So even though supermassive black holes exist, they're a tiny, tiny fraction of the total mass of a galaxy. They're not an important part of the dark matter. The remaining possibility for black holes is that, in fact, we could have primordial black holes. We could make black holes not from stars collapsing or from things collapsing at the centers of galaxies, but some process in the very, very early universe creates black holes that are very tiny. That is something that is actually completely plausible in terms of dark matter candidates. We have no way of ruling out the possibility that the dark matter is tiny black holes. If these black holes formed before Big Bang nucleosynthesis, they would not count towards accounting of ordinary matter in the universe. However, once you make the black holes out of once you make the dark matter of tiny little black holes, it's practically indistinguishable from making the dark matter out of particles. They're individual little objects. They're not big stellar-sized things. We can't look for them using microlensing. So we're back once again to the possibility that the dark matter is particles. And what we're going to do in subsequent lectures is go through all the different possibilities of ways to make particles that would count as dark matter. Black holes are one possible candidate for dark matter candidates that are basically particles. They're very tiny little black holes. It turns out that they are not among the most promising candidates. The reason why they're not the most promising is we don't know how to make them. We don't have a theory of black hole production in the early universe that would predict a large density of tiny black holes today. The best candidate theories we have for the origin of the dark matter are theories where we have a natural way of making them. So it turns out that the absolutely best candidate we have for making dark matter is something called supersymmetry, a new particle physics theory that naturally gives rise to a set of particles that are stable, massive, and weakly interacting, exactly what we want the dark matter to be. There are other candidates. There are the black holes we mentioned. There's a particle called the axion. There's even neutrinos, which are in the Standard Model. For neutrinos, there's a good reason why we don't like them. They're hot dark matter. The other particles are cold dark matter, but they seem to be less plausible from a particle physics point of view than supersymmetry does. However, we are keeping an open mind. We don't yet know what the dark matter is. That's part of the excitement of the next 10 years of cosmology. We'll be pointing our finger very specifically on where the dark matter comes from.